Good afternoon. So this is our development and growth. Today, we are going to work on an analytical framework that we're going to use for the rest of the semester to understand the sources of economic growth and the causes of economic growth. Okay, so let me now share my screen. Okay. Now, first of all, I'm going to spend some time on refreshing your mind concerning differential equations and defining growth rates and related issues. Okay. Now, obviously, when we start thinking about economic growth, we work with dynamic models. Okay, and in these dynamic models, we will denote time by t. Okay, and time, of course, will be an element in this set H, and we call this history, right? Now, history, so depending on whether time is continuous or discrete, okay, H, of course, will differ, right? In continuous time, H will be a subset of the real line, right? So time will be passing through instants, right? There will be no hole. Remember the real line. There is no hole, right? So suppose that this is 0, and suppose that this is t, right? So that could be your H, for instance, right? Starting from some initial date and extending to some final date, t, right? So this would become your history. When time is discrete, this is a subset of integers. Okay, this is z, the set of integers. So it is like 0, 1, 2, 3, right? And that goes on. It can come from negative numbers, -5, -4, -3, -2, -1, 0. So that doesn't really matter. But what matters is that time is now, so here we are talking about instants. Okay, here we are talking about periods. Okay, so that's an essential difference, right? And now suppose some variable x. Okay, so that could be GDP, capital, labor, technology. So some variable that changes in time, right? Now, most of the time, of course, we are interested in the growth of this variable. Okay, so we want to calculate the growth rate of this variable. Okay, now to do that in continuous time, so let me draw the line here. Okay, so to do that in continuous time, we look at this. So first we define the time derivative. Okay, the time derivative is basically the derivative of xt with respect to time, right? And then the growth rate of xt is defined in the following way. Okay, now what do you see here? What you see here is that there is this instantaneous change in x, right? So this is the total amount of change. You can actually write this as dxt dt, right? And then you basically take the proportionality relationship between the change and the existing level, right? If you remember the definition of the derivative, right? And if you apply it to time, this would give you the instantaneous growth rate. Okay. Now in discrete time, of course, the situation is a bit different. Why? Because now the change will be defined in this way, right? The change will be defined in this way, or equivalently for the previous period, it will be defined in this way, right? So what is growth rate? The growth rate will be this change again. Look at this definition here. That's the same. The change divided by the existing level, right? So these are some of the fundamentals, right? But now, so let me stop for a moment. Do you have any questions? This is all very simple, right? I mean, you remember all of this from your mathematical economics classes. What I'm showing you here is that time can be continuous or time can be discrete. It doesn't really matter. Most of the time, our toolbox is, flexible enough to be used in any way, okay? Because there is a certain correspondence between change in continuous time, so this is instantaneous change in xt from one instant to the next, and here there is a periodic change, right? The change in x variable from period t to period t plus 1, okay? And the definitions are, the definition of the growth rate is almost identical. Now, xt, of course, will be a function of time, right? And usually we are going to be interested in real numbers, right? So actually, here x is a function of time. That's important. Remember the definition of a function. I can write this derivative only because x is defined as a function of time, right? Otherwise, this derivative is not meaningful, okay? So that was the first thing. Now, let me show you a couple of rules about growth rates, okay? And here for now, I'm going to use a continuous time framework, all right? So there's time. Time is an element of history, and history is a subset of real life, okay? Now, one thing that is very interesting is this, and very useful, obviously. Now, suppose that I define a variable of time in this way, okay? So z variable is the multiplication of xt and yt. And these x, this x and this y are also functions of time, okay? Now, if that's the case, we have this very nice relationship between the growth rates of these three variables, and that reads gzt equals gxt plus gyt. Okay. Now, can you prove that? Yes, of course. If you sit down, take a pen and paper, you can actually do that. The trick is that you want to write, of course, this is z dot divided by z, right? This is x dot divided by x, and this is y dot divided by y. If you write the derivative of this, you start with z dot, then you realize that the relationship will follow, okay? So that's one interesting and very useful property. Now, as a corollary, you should be realizing that zt, when it is defined as the ratio of xt and yt, you will have this, right? Minus gyt. The proof is the same because yt, I mean, you can write yt as yt to the minus 1, define yt as wt, and then you do the rest, okay? Another property is this. Suppose that you define zt as the multiple of a constant and another variable xt. So here, alpha is constant. Okay. Now in this case, the growth rate of z will be equal to growth rate of x. Okay. Why? Because z divided by x is alpha. It's a constant, right? So if x is growing, z must be grow at the same rate so that z over x remains constant, right? Okay. So is it too late? You know, is there a synchronization problem between my voice and the visuals? Is there a problem? Like no problem. Okay, maybe some of just a little. All right, that depends on the connection, I guess. I mean your connection as well. So bear with me if the the delay is too large, just let me know and I can go back to the slide. Okay. So let me continue then. So there's another simple rule that we frequently use, and it's like that. Suppose that you define z in this following way. It's an exponential function of x, right? So it's like it's a power function of x. Suppose that this is beta, all right, where beta is constant. Okay. Now in this case, the growth rate of zt is beta times growth rate of xt. Okay. Now you see the logic. It's all about the chain rule, right? I mean, you can use the chain rule. First, you're gonna write z dot, right? I mean, let me just show you here. So it will be beta x, beta to the -1, x dot, right? So that's basically the derivative, the chain rule. Then you realize if you divide it by z, so what do you have? You have z dot divided by z is equal to beta, x beta -1 x dot divided by x beta, right? So what do you have? You have beta x dot x, so you have beta g of x. Okay? So that kind of logic will be applied to all other stuff. Okay? Now, why are these important? Because these rules are going to be used when we are trying to obtain growth rate of multiple variables, when the production relationships tie them together. Okay, so that's pretty important to get. And again, we're gonna frequently use such rules of growth rates. Now, in discrete time, though, the situation is a little bit different. Now, suppose that we are looking at a discrete time version. Okay. Now, in discrete time, once again, you can define a variable zt as xt, yt, right? Now, what you are interested in is to write this growth rate. Okay. This is the percentage growth rate of z, right? This is g of zt. Now, obviously, you want to write zt plus 1. So what is zt plus 1? Zt plus 1, by definition, is this, right? Then what is zt? Zt is xt, yt, right? And you have -1 here. So what do you see here? Well, now you have the gross growth rates. Okay, let me write it clearly here. So you have xt plus 1 divided by xt, yt plus 1 divided by yt minus 1. Now be careful. This is equal to 1 plus g of xt, right? And this is equal to 1 plus g of yt, right? Because these are percentage rates, this is gross rate. This is percentage, this is gross, right? So how do you write GZT? Well, GZT will be written in this way. You have 1 plus GXT times 1 plus GYT minus 1. Or, more intuitively, you can write this. Oops. You can write like this, okay? So in discrete time, these rules will be a little bit different, okay? So conceptually they are the same, but algebraically they're a little bit different, okay? You should be careful with that. And I'm leaving you as an exercise for you to work on the other rules, okay? Let me just show one of them. Yep, go ahead.
Where does -1 comes from?
Okay, it comes from here. So when I define the variable, the growth rate of a variable in discrete time, I do this, right? Oops. I do this, right?
I got it. Thanks.
All right. So I have ZT plus 1, ZT minus 1. Now, let me show you one example and you do the rest. Let me show you this one. If ZT is a power function of xt, okay? So what's happening here? Obviously, again, I want to write ZT plus 1 divided by ZT, right? So what is ZT plus 1? It is xt plus 1 to the beta. And what is ZT? It is that. So what do I have? I have xt plus 1, xt to the beta, right? So 1 plus gzt equals 1 plus gxt beta, right? That's it. That's very, very simple. So I'm showing you these things because you're gonna use them in your assignments, in class meetings. We're gonna see models, growth models, and in the growth models, of course, we're gonna be looking at such growth rates. Now, finally, let me also remind you something about differential equations and difference equations, okay? Now, first of all, if time is continuous, okay, this is continuous time. In continuous time, we will have differential equations, okay? And in discrete time, we will, so this is discrete time. In discrete time, we're gonna have difference equations, okay? Again, these are conceptually the same thing, but the algebra is different. Why? Because time is different. The formulation of time, the definition of time is different, right? So let me show you a couple of stuff. The simplest differential equation, so let me look at the continuous time model here. The simplest differential equation is this. Xt dot equals, let's say, alpha xt. Okay? And here alpha is some constant. So alpha is some real number, a constant. Okay? Now, what does this equation tell me? Well, this equation tells me that the change, the instantaneous change in x, what you see here, right? So this is instantaneous change, instantaneous continuous change in x, okay, this change is a function of x itself, okay? This change is a function of x itself. Now, the problem here, of course, is this. I don't know this function yet, okay? So xt as a function is not known, okay? That's the problem of differential equations, okay? My purpose is to use the differential equation to find the solution, okay? So the solution of the differential equation is this function, all right? Now, sometimes we can do it by hand, analytically. We take a pile of paper and we take our nice pens and we do some calculus and some algebra to find xt using the differential equation. In some other differential equations, we use numerical methods, okay? So in the scope of this classroom, in this course, we're not going to do numerical stuff. And most of the time, we're going to be interested in very simple stuff that we can actually solve by hand, okay? Now, so what is the solution here? How do we find the solution here? Well, it's very simple. First, imagine you are writing this as, so this in this way, right? Alpha xt, okay? Then you have, I mean, you can write this as dxt divided by xt times 1 divided by t equals alpha, right? Remember this from your mathematical economics classes. Now you can take the integration of both sides, right? Let me just do this with a different color. So you integrate both sides in time, right? Remember this? So dt's cancel out. Now dxx is what? Huh? So dt's cancel out, these terms, these are canceling out. On the left-hand side, I have dxx, right? Right? And on the right-hand side, I have alpha dt. So how do you solve this? Huh?
The left side is equal to x plus c. I guess.
This, no, not x. So it must be natural logarithm of xt, right? Plus some constant of integration. And this part will be what? Alpha t plus another constant of integration, right? But these are not very important. So eventually what you find is xt equals, sorry, ln xt equals alpha t plus c, right? Some c. C is some real number, right? So from this, you realize if you exponentiate both sides, you realize xt will be e to the alpha t plus c, or I don't have much space here now. So xt will be some constant alpha t. Right? You must remember this from your mathematical economics classes. Anyhow, so I need 15 minutes or so. So let's meet at 1:55. Okay? 1:55 after the break. Okay? Everybody hearing me, right?
Okay.
All right. Let's meet at 1:55, about 15 minutes later. Okay, bye.